All right, so we'll continue on this topic of hypothesis testing. And so there's this very important concept called a p-value, okay? And I'm going to write down the definition for the p-value here. And then we'll talk further about this, okay? So the p-value is the probability of observing our data and we also write or something more extreme if we assume the null hypothesis is true. Okay, it'll be very important for you to understand this concept of what a p-value is. Okay? So earlier at the end of our quote example of things, I said, you know, the probability of observing a p-hat equal to 0.4533, which is basically our data, right? The probability of observing a p-hat of 0.4533 or something more different okay, more different than or more different from 0.4, okay, if we assume p is equal to 0.4, so this is if we assume that the null hypothesis is true. This probability, that probability is 0.1836. Okay. And then I said 0.1836 seems large to me, okay? Or we'll say is large or is not small. Okay, is large. And what I mean by is large or is not small, what we mean by that is it's not an amount we can ignore, okay? It is not small enough for us to ignore. Okay, and because it's not small enough for us to ignore, what we're going to say is that we will not ignore the possibility that our data was a result of random chance alone. Okay, so in our case, so if the p-value is large, then that means our data could have been a result of, is quite possibly the result of random chance random chance only. And therefore we would say, you know, we do not reject our belief that the null hypothesis is true. Does that make sense? Okay, so, you know, you look at 0.1836 and you say, well, that doesn't seem big, but it's non-negligible, okay? And so there's this question of when is our p-value big and when is the p-value small, okay? And so at the beginning of our experiment, we pick an arbitrary value called alpha. Did you guys get all this down? Can I flip to the next slide? Okay, so, you know, when is our p-value, quote, large or small, okay? So at the beginning of our test, we pick an arbitrary alpha. Arbitrary value called alpha. Okay? And this is going to be the line. If it's bigger than alpha, it's large, okay? It is, quote, large, and that means we do not reject, you know, the belief about the null hypothesis. And if the p-value ends up smaller than alpha, okay, it is small, and that leads us to we reject our beliefs about the null hypothesis. So I'll just write we reject the null. Okay, and just over time, you know, the most common choice for alpha is 0.05. Okay, it's kind of the most common choice for alpha, and I think it's 5% because we use a decimal system based on the fact that we have 5 fingers, right? Or 10 fingers on our 2 hands. Should it be bigger than that? Should it be smaller than that? It's probably 5% is probably a good number to use, but there's nothing actually magical. There's no mathematical property that says it should be 5%. It's just, you know, something around 5% is probably the correct value to use, but it's really just an arbitrary value, okay? Kind of, but, you know, we go off of this and, you know, we deal with arbitrary values throughout our lives and we just accept them as like, oh yeah, of course, naturally, this is the case. Such as the age of majority in the United States is 18, okay? On your 18th birthday, suddenly we entrust you with legal decisions, you know, now you can choose to buy cigarettes. Well, maybe that'll change to 21, I don't know. You can fight in the military and whatever you want to do, right? At 18, you know, is there something magical that happens on your 18th birthday? No, okay? Should the age of majority be somewhere around 18? Probably, because studies have shown that, I don't know, your prefrontal cortex is somewhat developing or finished developing around that time, and by then you're able to understand consequences and things like that, but who knows, right? But we just kind of have accepted that, okay? And then you get this visceral response now when you hear about a crime committed against a 17-year-old versus a crime committed against a 19-year-old or something like that, right? You feel like the crime against the 17-year-old is much worse than the 19-year-old, just because we've established this line, which we have to do in society and in order to function, and in statistics we have to establish some arbitrary value, such as 5%, which is probably a good value, but if we wanted to, we could choose a different value, okay? So the most common choice for alpha is 5%, but we can use alpha equal to 0.01, or use alpha equal to 0.10, or anything in between, really. Okay. All right, so again, this all fits in with the notion of, did what we observe is that significantly different from what we expected, or is it not that different? Okay, so let's for example, let's just talk about all of this p-value stuff. All right, so let's say we'll play a game, okay? We play a game, all right? And in this, you're just gonna flip a coin. Flip a coin, and then, and if it lands heads, you win. And if it lands tails, your opponent wins. Okay, so let's say you and your opponent play 20 games. Okay, and let's say the opponent wins 12 games. Okay, would you and your opponent play 20 games? Oh, here's the catch. Okay, the opponent does all the flipping. Okay, opponent flips all the coins. Opponent does the flipping. Okay. After 20 games, the opponent has won 12. Do you think that the opponent is cheating? What do you guys think? Would you accuse your opponent of cheating at this point? Probably not, right? You just say, you got a little lucky, right? Because winning 12 times out of 20 is quite possible if the opponent was playing fair, okay? Do you think the opponent is cheating? Probably no, okay? Could the opponent be cheating? Yeah, the opponent could be cheating, but we were going to say, we can calculate the probability, or we can say, we would say, even if the opponent is playing fairly, the opponent plays fairly, there is a reasonably high probability that he gets 12 wins out of 20. Okay, can we actually calculate the probability of him getting 12 wins out of 20? Or more? 12 or more wins out of 20? Yes, we can, right? So in this case, we have n equal to 20, okay? If the opponent plays fair, we can say our null hypothesis is that the probability that the opponent wins is 0.5. Okay? And what we observed, our p hat was 12 out of 20 wins. We get a p hat of 0.6. Our standard error is the square root of 0.5 times 1 minus 0.5 over 20. We have a standard error of 0.5 times 0.5 divided by 20. What is that? 0.111. Or 0.112, it doesn't matter. Okay. Now we'll say 0.1118. Okay. So my z-score, so we're expecting 0.5. What we observed was 0.6. We want to know what's the probability of being over there. We do 0.6 minus 0.5, and we divide by 0.1118. And I get a z-score of 0.89, 0.89. And we can look up the probability of being greater than 0.89, which is going to be 0.1867. So here our p-value is 0.1867. So if you play someone 20 games of this coin flip thing, just from random luck, that person might win 12 games or more. And that's going to happen about 18 or 19% of the time. Okay? And so because it happens, you know, about 1 in 5 times, we're not going to accuse the opponent of cheating. Is that okay? All right, so the opponent won 60% of the games. You know, that's a little bit higher than what we would have expected, right? So currently our belief about the world is that the opponent is playing fairly. So we're expecting the opponent to win 50% of the games. The opponent ended up winning 60% of the games. Is that very different from what we expected? According to the math, 60% is not that different from 50%, okay, when we're talking about 20 games. All right, let's try the same thing again. So this time you and the opponent play 500 games, okay? That's too many. All right, we'll say 200 games. Okay? You and the opponent play 200 games, okay? We'll say opponent wins 60% of the games again. Again, the opponent does all the flipping, okay? Do you think the opponent is cheating now? Okay, and the answer is maybe. All right, let's do the math. Okay, so what we're going to do is our null hypothesis is we're going to assume the opponent is playing fairly. Okay. Okay, and what we're going to, our alternative is that whatever the opponent is doing, he's giving himself an advantage. I'm using the greater than sign and not the not equal sign. The reason for the not greater than sign is because it doesn't make sense for the opponent to give himself a disadvantage, right? Like, so if the opponent only won 40% of the games, we would not accuse him of cheating, right? We would just say, oh man, that really sucks for you. But thanks for flipping the coins. We would not accuse the opponent of trying to cheat if he only won 40% of the games. Okay, so here we're only interested if the opponent is giving himself a win rate of greater than 50%. Okay, we observed p hat equal to 0.6, and we are using an n equal to 200. Okay, so if the null hypothesis were true, we would expect to be at 0.5. What we're seeing is we're out at 0.6. Okay, so our standard error in this case is going to be the square root. If the null hypothesis were true, it would be 0.5 times 1 minus 0.5 divided by 200. Let's try that out. 0.5 times 0.5 divided by 200. Okay, I'm getting 0.0353. This is our 0.35355. Okay. So my z-score is 0.6. This is what I observed. What we're expecting is 0.5, and we're going to divide by our standard error. So I'm going to do 0.6 minus 0.5 divided by the previous answer. And so my z-score is 2.83. I'm 2.83 standard errors away from the mean. Okay, so that seems like what we observed is quite different from what we expected. Right? This time 60% seems to be quite different from 50%. Okay, we can look up 2.83 in our z-table. So 2.83 is 0.9977, meaning that we have 0.0023. Okay. All right. So what this means, so my p-value is 0.0023. Does that seem small to you? Yes. Okay. If we were to use the arbitrary line of 5% as what's big and what's small, this is definitely smaller than that. Okay. So what does this p-value mean? Well, what it means is that, is it technically possible for the guy to win 60% of the games just from getting lucky? Is it possible that he was playing fair and he just happened to win 60% of the games from random luck? Yes, it is possible. How often does that happen? It happens pretty rarely. It happens with probability 0.0023. Okay? So at this point we can give him the benefit of the doubt and say, wow, you happen to be one of those 2 in 1,000. Or we can say, I don't think you were one of the 2 in 1,000. I think you were doing something funny with the coins. What do you think we should conclude? We're probably going to conclude cheating, right? But it's technically possible. It's there. You run the risk that you're accusing your opponent of cheating when he was actually playing fair. But we're saying, the probability that he would win 60% of the games from playing fair is so small. It's only 2.002, less than 1%, that I'm ready to ignore it, and I'm going to say, I think you're cheating. Okay. So what does this p-value mean? It means, could the opponent win 60% of the games from fair play? Yes, but it happens with a very low probability of 0.0023. Okay, so we will kind of ignore this possibility and conclude he cheated. Is that okay? Okay, and so notice in the previous example, he also won only 60% of his games. Or in this example, in the previous example, he won 60% of his games. But in the previous example, we did not accuse him of cheating because we said that, you know, after 20 games, you can win 60% of the games with a probability of 0.1867. So we said, well, that happens often enough that it's possible that he just got this from being lucky. In this case, after playing 200 games, the probability of winning 60% from just random luck is much, much smaller. So we were ready to accuse him of cheating. Okay? All right, so let me break down this process for hypothesis testing into kind of 4 steps. Okay. So number 1 is make your hypotheses. So our null hypothesis is that P is equal to some number, and I'm going to call that number P0, okay? So maybe you're expecting the proportion to be 0.3, okay? And then the alternative is P is not equal to P0, or P is greater than P0, or P is less than P0, okay? So some notes. The null hypothesis will always have an equal sign. Okay. The null hypothesis will always have an equal sign. Okay. And then the alternative hypothesis is identical to the null hypothesis, except replace the equal sign with a not equal, or a greater than, or a less than sign. Okay? General rules. Okay? If the question says something like, do we have evidence of a difference? Keywords like difference, or has changed, or not the same, something like that. Use the not equal sign, okay? If it asks evidence that, you know, it is larger, bigger, greater, use the greater than sign, okay? And evidence that it's less, smaller, fewer, okay, use the less than sign. Okay, so that's how you establish your hypotheses. It's okay? All right, step 2, check your hypotheses, okay? Now, in quizzes and stuff, I will not ask you to check your hypotheses as part of this thing. I'll have a separate set of questions for checking hypotheses. Check your hypotheses, choose your alpha, okay? And if no alpha is given, assume, choose, or I should say identify alpha. If no alpha is given, assume alpha equals 0.05. Okay, step 3. These are your calculations. Okay, and the calculations can be broken down into 3 parts. 1, the standard error. So step 3a would be our standard error, okay? The standard error is going to be the square root of p0 times 1 minus p0 divided by n. 3b is our test statistic, okay? Over here I should say p0 is the p in the null hypothesis. Okay, the test statistic here is going to be a z-score. This is the difference between what we observed minus what we expected divided by the standard error. So in this case it's going to be, we observe a p hat, we subtract the p0 in our null hypothesis, because that's what we expect if the null hypothesis is true, and we divide by the standard error from the previous step. And then the calculations, 3c is find the p-value by looking up the test statistic in the z-table. In the table. Okay? And so there's a few things. Okay, so this all depends on the alternative. So if the alternative has a less than sign, your p-value is equal to the area to the left of z. Okay. If the alternative, so I'll draw the picture this way, area to the left of z. Okay. If the alternative has a greater than sign, the p-value is equal to what? The area to the right of z. And if the alternative has a not equal to, the p-value is 2 times the tail area. Okay, so you're going to find tail area is basically the area to the left of z if it's negative, or the area to the right of z if it's positive. So what this looks like, take the area to the right and the area to the left. So those are your calculations. That's okay. And then lastly, did I flip too soon? Okay. All right. And then once you have your p-value make your conclusion based on, make a conclusion by comparing your p-value to alpha. Okay, so if the p-value is greater than alpha, this means the probability of getting our data from random chance was high. So we will not doubt our beliefs. So that means we do not reject the null hypothesis, okay? Or in other ways, we say we do not have evidence to support the alternative, okay? Or the other possibility is if the p-value is less than alpha, okay? This means the probability of getting our data from random chance is low under the null hypothesis. Okay, so that means we reject our null hypothesis. We have evidence that H0 is false. We have evidence to support the alternative. We can also say, you know, our p hat is significantly different from p0. There's one more topic I wanted to cover, but we've run out of time, so I'll have to cover it on Wednesday. Okay, I will post some, I already have homework posted, homework for chapter 8 posted. I'll post a kind of a practice quiz for Wednesday, and you guys have a quiz on Wednesday covering chapters 7 and 8. But I think if you study the practice quiz and understand that, you'll be in good shape. Okay, we'll see you guys.